Hello. Previously, we started by saying that the mechanical response of a polymer depends on both temperature and time. In the previous videos, we have seen what are the temperature effects on the response of the polymer. In this video, we will see what are the time effects on how it changes the responses in the polymer. So, first we will start by discussing about how do we test these polymers. So, let us say if we test like metals, usually for metals we test it using either tension test, compression test, but mostly uniaxial tests. So, let us say we do this tensile test. When it comes to polymers, it should be done or planned very carefully. The reason is because depending on how fast or how slow we are loading the specimen, the behavior can change in polymers. So, as we can see here, we have this brittle behavior, we have this semi-ductile, and then this ductile behavior. So, let us see under what conditions we get the brittle behavior and under what conditions we get the ductile behavior. So, what we are trying to say is this tensile behavior greatly depends on the loading rate, and we will now see the conditions on which it depends. So, for brittle materials, let us say we are testing PVC material. So, when we are testing at fast loading rates, what we see is the material when we load, it fails or responds more like a brittle material. The same PVC, when it is tested at moderate loading conditions or very small loading rates, then we get this semi ductile, and if it is even slower, we actually get this ductile. So, we are saying this happens when the loading rates are low and brittle we see when it is fast loading rate. Okay. So, what have we seen? We have seen that for a polymer, of course, it is strain rate dependent because we are talking about the fast at which the strain changes, that is the input in the material, and the output is the response or the stress variation in the material. So, we have seen that these polymers are highly sensitive to the strain rate. So, these tests should be planned carefully. So, instead of doing these uniaxial tests, what kind of test we should do for polymers such that we can capture these time dependency well. For that, usually people do either the relaxation test or a creep test. We will go in greater detail about this relaxation and creep test and see how the response is different. But this can also be done using dynamic tests where you can apply a cyclic load or a cyclic strain and then measure the response. But this is not what we will be looking at in this week. The dynamic test we will be looking in a different week, but in this video we will look at the relaxation and creep behavior and how it changes with time. So, let us start with this relaxation test. So, as we can see, this is the input we give to the material. So, we take a specimen and then we apply constant strain quasi-statically. What it means is, let us say we are taking a polymer specimen, I apply a stretch, let us say this stretch is fixed 5%, 10%, when after stretching I hold it, meaning now there is no movement or deformation in the specimen. But what we do after this is we measure what is the stress, because once we stretch it, the specimen wants to go back to the original state, but then since we are restricting that movement, then there is stresses produced in this specimen. So, that is what we are measuring. But let us pay attention to what we meant by this quasi-statically. What we mean is, though I say that this displacement has to be applied quickly, but it should not be quick enough so that there are inertial effects. So, we need to avoid those inertial effects when we apply the strain. But there are different ways we can do the test. The example which I am trying to explain is a tension test, but of course, the same sample, instead of stretching, I could have compressed by an amount and hold it there. Then we say that it is a uniaxial compression. Similarly, I can also do like at one end you hold it and at the other end you twist it by an angle and then hold it. Once you hold, you measure what is the resultant stresses. So, these are all relaxation tests, either it is tension relaxation, compression relaxation or the torsion relaxation. So, we are also mentioning, in addition to there are no inertial effects, the specimen should not have any history. Now that we are talking about materials which are time dependent, which means let us say this specimen I have tested it yesterday and then today morning I have planning to do this tension relaxation test. But since it is loaded yesterday, there is some history still in this specimen, which means maybe there are still some molecular rearrangements which are happening, which you cannot see macroscopically, but microscopically these are still happening, and if given enough time they will show their effect either in stress or strain. So, we need to have a specimen where this history is not present. Usually what we do is there are some means where you can remove the history, something like annealing, where we are trying to relax all the internal stresses or these history, the effects of the history on it. Okay. So, now let us see, we have only talked about the input till now, saying that we apply a constant strain. But what is the response to this constant strain? So, once we apply this strain, then it forces the molecular structure, which means the molecules, they are forced to take a new shape because of the externally applied strain, right. Once they take the new shape, of course, there is resistance to this taking the new shape, and this is seen by the stresses developed. So, we were discussing about here, saying that at time t equal to 0, where we applied an instantaneous strain, there is an instantaneous stress developed. The reason for this instantaneous stress development is because we are forcing these molecules to take the new shape, and then there is resistance for this movement. But then we are interested in what happens if we wait for a long time. If we wait for a long time, what happens is these molecules, they rotate and unwind. Basically, now we have forced these molecules to take a new position, but given time, since there is this rotational freedom at the carbon atoms, it can readjust its molecular structure such that the same shape can be attained with less stress, or it is trying to go to a more equilibrium position. So, that equilibrium position will be attained with less stresses because it is readjusting to the new loading scenario. And then as we can see that there is a, with time the stresses decrease. Now, the question is, there are two possibilities the way these stresses can come down. Either they can come down all the way to 0 if you wait for a very long time, or they can come to a constant value such as shown in this curve. So, let us say this is curve 1 and curve 2. Curve 1 is when it is coming to a constant value, let us say at a very long times, and in curve 2 it reaches 0. Now, let me pose you a question. So, thinking about thermoplastics and thermosets, which of these will go into curve 1 and which of these will go into curve 2? right. So, let us start with thermosets. Which of these curves will it take? The answer is thermosets will go to a position where, because in thermosets as we know it is a networked polymer, meaning there are cross links. So, once we stretch, the stretch happens between these cross links, but then once you given time, these molecular chains are readjusting. Though they are readjusting, it is not like these polymer cross links can move. So, because the cross links are limited in their movement, finally it comes and settles down to a constant stress, even though you give infinite amount of time. But for thermoplastics it is slightly different. So, in thermoplastics as we know, these molecular chains are bonded by secondary bonds. So, once we stretch it, either between entanglements there is a stretch happening in the molecular chains, but given enough time what happens is these molecular chains can slide past each other and then reduce the stresses. But if we give enough time, what happens is it flows. So, initially it might be a counterintuitive for us to think how can a solid polymer like thermoplast flows, but we are talking about when it is given very long times, actually these polymer chains can slide against each other upon stresses, and because of this we get this flow, meaning it comes to a zero stress state at long times. Okay. So, now let us define how can we talk about modulus. We have seen the input strain and the output stress, but how do we now define the modulus? So, as we can see, strain is constant, stress varies with time. So, by going by the definition of modulus is stress by strain, this modulus is changing with time. So, that is why we need to write it as a function of time t. Same thing with the stress. Here epsilon naught is the input strain. Okay. But we can also talk about what is the modulus when time t equal to 0. When time t equal to 0, we call it as the initial modulus, because then we are talking about E naught is simply stress at time t equal to 0 by epsilon naught, which is the initial strain applied. Similarly, we can also talk about the equilibrium modulus. Here we are talking about when time approaches infinity or very long times. So, here the E infinity or the equilibrium modulus is given as stress when time approaches infinity divided by strain which is applied. So, this is the way how we can discuss about the response of a material during the relaxation test. Now, let us continue this discussion for the next test, which is the creep test. So, creep is very close to the relaxation. The only difference here is our input is stress. So, what we are now doing is we are applying a constant stress. So, let us think of an experiment like this. Let us say this is the specimen to be tested. I hold at one end, and at the other end I apply a dead weight. When I apply a dead weight, which means that the load is constant or the stresses in this specimen are constant. The only difference is if we give more time, initially when we apply the load there is some instantaneous strain or the initial strain, that is the deflection coming from the specimen, but if you give more and more time the specimen elongates. So, this elongation is nothing but the creep behavior. So, again when we are talking about testing polymers, we say that we are applying a quasi-static load, meaning that there are no inertial effects, and of course, even this creep test can be done in tension, compression and torsion, just like how we discussed for relaxation tests. And again I need to mention that the specimen care should be taken that there is no loading history or if there is any loading history, there is some mechanism where we are trying to remove that history either through annealing or other means. Okay. But now let us see what is the response for this creep load. So, we said at time t equal to 0 there is a deformation, but as we wait long give more and more time, the elongation increases. So, essentially what is happening is initially these molecules molecular chains have taken a new position because of the load, but then since there is more time, again they rotate and rewind. Once they rotate and rewind, we know that it can now take the deformation is larger, so it can take large strains. So, this is at time t equal to 0 where we said there is an instantaneous increase in the strain. This is just like elastic materials like steel, right, or aluminum. So, when I apply a instantaneous stress, there is an instantaneous strain, and usually this instantaneous what we are talking about is in the order of 10 power minus 12 seconds. So, we simply call it as instantaneous because there is no gap between your loading and the response. So, we are talking about what happens at time t equal to 0. Okay. So, as we wait, we said the strain increases, but now again there are two possibilities, which means either the strain response can take this curve 1, meaning that the strain increases and reaches a constant value at long times, or there is another possibility that the strain keeps increasing. So, it never stops, it keeps on increasing. So, let us say initially it is a nonlinear curve, but towards the end it reaches a straight line, meaning the slope is constant. So, now again I will ask the same question the way we discussed in relaxation test. Which of these curves is for thermoset and which of these curves is for thermoplast? So, if you think carefully, we said thermoplastics, especially if you give more time, these polymer chains slide against each other, which means if you think about it, it is more like a fluid, right. If we think about it more like a fluid and we are saying there is continuous load, how do we expect that strain to be? We expect that strain to keep on increasing. There is no reason for the strain to stop or to reach a constant value. So, this should be our thermoplast. And for thermosets, if you keep stretching this specimen, we are now talking about crosslinks which are present in the molecular structure. Because of these crosslinks, once these crosslinks are enough stretched, there is no further movement which is possible, because if you stretch even further, the carbon backbone needs to be broken, or there is a limit at which the carbon backbone also can stretch. So, it reaches a constant value for thermosets. Okay. Now, again let us think of previously we were talking about relaxation modulus to capture the behavior, but for a creep, how do we capture this behavior? For this we define what is called as creep compliance. So, we are defining with this variable d, we are saying it is a function of time, and the definition of compliance is strain by stress. In this test, which is constant, stress or strain? We said that stress is constant, which is sigma naught, that goes in the denominator, and in the numerator is our measured quantity, which is the strain which changes with time. So, again we can look at two different types of compliances. What happens at time t equal to 0? At time t equal to 0, we said that there is an instantaneous or the initial strain. So, we get this initial compliance represented by d naught. So, we are discussing about what happens at time t equal to 0. So, d naught is our strain at time t equal to 0 divided by the input stress sigma naught. Okay. And the equilibrium compliance is what happens when time approaches infinity, which we define as d infinity or equilibrium compliance, which is given as epsilon at time approaches infinity divided by the applied stress sigma naught. So, the initial compliance and the equilibrium compliances talk about the two extreme responses of this polymer, but intermediate it is a nonlinear curve, which again depending on the polymer and depending on the load we apply, this change. So, currently we are only discussing about in a qualitative sense how the response is, but in coming weeks we will discuss more into trying to capture the equations which define this behavior using some specific models. Okay. So, now that we have looked into the relaxation test and the creep test, there is an other test which commonly is used, which is called the creep recovery. So, it is very close to the creep test, because even like in creep test you apply a constant load, but the only difference is, let us say around time t equal to t1, after a while you just remove the load. So, means the load goes back to 0. Let me repeat it one more time, saying that between times t naught to t1, so which means t naught is our time 0. So, from initial to time t1 we have this sigma equals to sigma, and if time is greater than t1, again the stresses go back to 0. So, this is the loading or the input we apply for a creep recovery test. Now, let us see how the response is. So, initially this response is very close to a creep test. So, since we are at the initial portion, it does not matter whether we are discussing about the thermoplast or the thermoset, because depending on if it is a thermoplast it keeps increasing, but if it is a thermoset it reaches a constant value. But we are focusing on the behavior, what happens beyond this time t1. So, beyond this point when we remove the load, how does the polymer behave? Again it has two possibilities, either coming back to 0 strain or it can go back to a constant value. So, again there are two possibilities like C1 and C2. So, let me pose the same question again. So, which of these you think is the behavior of a thermoset and which of these is the behavior of a thermoplast? So, we said that thermosets are ones in which between the crosslinks the molecular chains they get stretched or rearranged, but once this load is removed they come back to the original position, because it is like an elastic material, you just stretch between the crosslinks and then after release of the load they come back to the original position. So, we are saying that these thermosets follow this curve C2, meaning that given enough time the strain comes back to 0. But in the case of thermoplast we said that these are a fluidic behavior, especially when we give enough time, which means they slide past other molecules. Once they slide past, which means that they have undergone some, I would not say plastic behavior, but then there is some residual strain which cannot be recovered. So, these are thermoplasts which even after removal of the load does not go to 0 strain, but there is some non-zero strain. So, we just said that thermosets reach 0 strain and thermoplastics reach a constant value. Okay. Now let us look at a concept called as isochronous modulus. So, the reason why we need to talk is because we said modulus is a function of time, right, but it is hard to discuss about modulus if it is a function of time, especially if let us say there is an other variable which is changing. Let us say we want to discuss how the modulus varies with temperature, then I need a single value for the modulus, right. How do we get that single value? That we get using this isochronous. Isochronous, as the name says, chronos means time, iso means the same time. So, for this we consider the relaxation test, in which we apply a constant strain as input, and for output we look at stress. The only difference now is here we need to specify a time. So, let us say that time we are specifying is T1. So, what we mean is at T1 we are looking at what is the input strain, and we are also looking at what is the corresponding stress. Okay. Once we have, now that we have only a single value of strain and a single value of stress, now we should have a single value even for the modulus. So, now the question is, what is this time T1? So, there is no one specific way to define it. Depending on applications, people have used like a 10-second relaxation modulus, means they have taken this T1 equals 10 second, and people have also talked about 1 minute relaxation modulus, meaning T1 is taken as 1 minute, and other possibilities also can be tried. But essentially what we are saying is, the moment I say whether something is E10 or E1, we are only discussing about a single value, because at a particular instant you only have a single value of stress and a single value of strain. So, let us go back to something which we have already seen in the previous videos. This is the modulus versus the temperature or normalized temperature. So, previously we presented this curve saying that the y-axis is modulus. At that time I intentionally did not mention what modulus we are talking about, because for a polymer there is no constant value for modulus, right. But what I did not mention then and what I am mentioning now is, actually this modulus is an isochronous modulus. Most likely it is E10, meaning the modulus after 10 seconds of loading. Okay. So, for example, here we are looking at variation with temperature. So, let us say you do an experiment, this is your experiment 1 and this is your experiment 2. So, basically you do 2 relaxation tests at 2 different temperatures. So, let us say this E1 is done at a very low temperature, let us say at 0 degrees, and E2 is done at a relatively higher temperature, maybe at room temperature. So, both in these 2 experiments what we are saying is, we apply constant strain and then we report the stresses at time t equal to 10 seconds. So, depending on the stress and strain, now we can give modulus values, and these are the modulus values we have obtained from the experiment. Okay, this isochronous modulus now helps us in comparing the modulus with different parameters. What we have shown here is temperature, but it could be anything, any other parameter. Okay. Now, let us summarize what we have discussed in this video. We were discussing about the time effects of the polymers. So, we started by saying that loading rate is very important when we design or plan a test, because when it is slow, for example, with PVC we have seen it shows a brittle behavior. Brittle behavior is shown when the loading rate is very high, but when the loading rate is low, then we see a ductile behavior. Then we also discussed about 2 important tests, which are the relaxation and creep test. in relaxation the input is the constant strain and we measure the stresses. We say we have seen that because of the rotation and unwind of the chains, the stresses reduce given more time. And we also discussed about the relaxation modulus, which we said is a function of time and it is given by stress by strain. Strain is constant and stress is a function of time. Similarly, for creep we said that the input is we apply a constant stress and measure what is the strain with as a function of time. Molecular mechanism wise, again these molecules rotate and unwind, that is the reason why once we apply a stress the strain keeps on increasing. We describe the response in creep test using creep compliance using this function d as a function of t, which is the strain divided by stress. Stress is constant sigma naught and strain is a function of time. Finally, we said usually when we want to compare modulus with any other parameter, we need a modulus value which is constant. We get that using this isochronous modulus, meaning that we are fixing the time and we are looking at what is the modulus at a specific time after loading. So, for that we define this E10 and E1, meaning that E10 is the modulus after 10 seconds and E1 is the modulus after 1 minute. Okay. With this we conclude this lecture. We will meet again in the next lecture. We will discuss about the failure of polymers. See you then.